Hey everyone, thanks for tuning into TestTube Plus today. I am Trace, and I'm here with my friend Kyle Tierman. Hello, Kyle. Welcome back.
Thank you.
Kyle is a surfer and also YouTuber, and he's here as our wave expert since he spent the most time around them. But today we're going to talk a little bit about what a wave is anyway. Make sure you check out yesterday's episode all about why waves are important. But today, what is a wave? Like, what are the different parts of a wave, Kyle?
Sure. So, the most interesting thing that will trip out your friend when you're looking at the ocean is you can point out to a wave and you can say, you know what? What's creating a wave is actually energy moving through water. Now, essentially, a wave, it's just like a sound wave. It's energy moving through water. It's not actually water traveling. Water travels to a certain degree, but really it's energy moving through that water.
Right, so it's if you see a wave moving through something, and it looks like the wave's moving up and then moving down and moving forward at the same time, but it's really just like a carousel.
Absolutely.
The horse is just going up and down in the same place. It's everything else around it that's going crazy.
Exactly. So waves are largely created by wind.
Okay.
Okay, and if it's blowing 50 square feet for 2 hours at 10 miles an hour in the middle of the ocean, who cares? That's not really going to create a storm. But if there's an area the size of Alaska blowing for a week with really strong winds, that's going to create a storm. And a lot of that is created due to low pressure systems. So you could think of it like two kids, right? One is hot air, one's cold air. They're on a playground and they're running at each other. And as soon as they hit each other, they hit a merry-go-round. That's the Coriolis Effect, the spin of the Earth. That's largely why storms operate in a circular fashion. They start spinning, and then that, depending on how fast the wind's going, is largely going to determine the fetch of the storm. That's
fetch.
The fetch. So the fetch is the given area that wind is traveling around open ocean.
So if a storm is, say, 100 square miles, and it's all open ocean and it's blowing across all that, the fetch would be that area.
And it's also the distance that it travels.
Oh, okay. So the storm is also moving.
Yeah, because the storm's also moving, so the fetch of the storm can be the distance it travels.
Okay.
So check it out. So now...
So we've got like the above thing. What about the wave part?
Okay. So now ocean waves operate in a very similar manner to sound waves. If I'm talking to you in this direction, you're getting what's called a transverse wave, right? My sound energy is oscillating up and down.
Through the air.
Through the air, right? Yeah. Air isn't the best conductor of energy. That's why my sound wave is going to stop at the end of the room. Yeah. Water is a much better conductor of energy.
Sure.
So this energy, these transverse waves are moving up and down. They're oscillating through the ocean. And that's what's creating, seemingly, these waves moving up and down. Now, how we measure waves is that the oscillation between the peak and the trough of a wave, the highest point
and the bottom.
The top and the bottom.
Pulling some math skills from like grade school here.
Right,
okay, got it.
So that is the amplitude of a wave.
Got it.
Right. So if I tell you that an open ocean swell is 8 feet,
that's an 8-foot wave.
That's an 8-foot wave.
From the top to the bottom.
That's the top to the bottom. Now, the second thing that you need to understand to really get this is that we're not only measuring the amplitude, but we're measuring the period. That's the period between the peak of one wave and the peak to the next wave.
Okay.
That largely is going to determine how powerful a storm is.
So amplitude is vertical distance of the wave, how tall the wave may be, and then the period is kind of how long that one wave is, in between that wave and the next.
Exactly. You can think of it like you drop a pebble in a pond, and from the beginning of that splash, you're going to get the highest amplitude and the shortest period between two waves. But as it spreads out, that energy is going to dissipate through it's going to dissipate, and the amplitude is going to decrease and the period is going to increase.
Got it. Okay.
Right?
So
because basically as a swell is traveling, you have atmosphere. It's like a hand. It's trying to push the ocean down. Mm-hmm. So the further it travels, the period's going to spread out, and ultimately the storm is organizing itself. Mm-hmm. And water is such a good conductor of energy that we have waves that will show up in California that formed below New Zealand, or up near the Aleutian Islands. Most of our northwest swells, these are the wintertime swells that we get, form off of the Aleutian Islands. That storm will be spinning down towards us. We'll get cold air from Siberia that'll push that storm forward. Mm-hmm. And then by the time it hits us, what originally started as, for example, this swell that's just hitting us right now, which is one of the biggest ever recorded, was 67 feet at 17 seconds. But by the time it's hitting us, now I think it's about 9 feet at 20 seconds.
Because so it got a longer period.
It got a longer
the same
period.
Amount of energy, maybe a little bit of dissipation, but it's now shorter. So that energy is moving faster to get along.
Exactly.
Crazy.
And by the time it hits us, it's going to show up as a different type of wave. Rather than if the storm was directly off of our coastline, mm-hmm. that wind's going to it's going to show up differently. Mm-hmm. So if I were to tell you now that it's 10 feet at 19 seconds, that means that, wow, that's a big period between the two waves. Mm-hmm. That means that it traveled from really far away. So right now we're talking about open ocean swells.
Okay. So if you look at a wave, you've got its period, which is its length. You've got its amplitude, which is its height. It's being created by giant storms, and it's being affected by the atmosphere, the temperature of the ocean, and all sorts of other different things. Like, what if we're not in the open ocean? What if it comes near a sandbar or a coral reef or, a continental shelf or, I don't know, I'm going to run out of oceany terms soon. So what happens if it hits something? Then what?
The size amplifies, because check this out. So you're picturing a wave oscillating through open ocean, right? And the bigger the period, the deeper that oscillation is going. It's maybe scraping across the ocean floor, it's going up, it's going back down, and then all of a sudden it hits a reef, so that energy has nowhere to go except up.
Right.
So you look at a lot of the biggest waves in the world, and they are so big because they have big canyons outside of them, so there's nothing to obstruct that energy from moving in. Like Mavericks, for example, one of the best big wave spots in the world, it's moving in from really deep water, and then it hits a reef that's shaped almost like a finger. So all of that energy is amplified, and say there's an 8 foot at 16 second swell, right? It's moving through the ocean. That'll show up as a 30 foot wave at Mavericks, because that energy has nowhere to go except up when it hits the reef.
Wow. So it has to kind of compress itself into this massive wall of water, essentially. And when it does that, this is a combination of processes from, like you were saying earlier, the Aleutian Islands or New Zealand, they can be so far away. And so that's not actually one wave, it's a combination of a whole bunch of different waves and storms and all pushing together. You used sound waves earlier. So if you were just standing yelling in a room, that's one thing. But if 20 of us were standing there all yelling in the same direction, that's going to make something humongous.
Right, you're getting what's called constructive interference, where waves are lining up together and increasing in power, right? It's like a football stadium, that's a lot louder than just a couple people yelling. And you get that in the ocean as well, right? There's a swell coming towards us, there's another swell that comes towards us. That's gonna change the direction of the original swell. It might amplify and create power. That's where you get rogue waves.
Okay, what's a rogue wave? I played a video game where I was a pirate and I had to deal with rogue waves, but that's all I know about them.
Well, rogue waves are what sink a lot of cargo ships.
Didn't sink my pirate ship.
Right.
That's all I'm saying.
But so check it out. You're on a cargo ship going through the ocean, specifically down places like Africa that have a lot of ocean activity.
Sure.
You're going over. It's 8 feet every 16 seconds. You're going up and
Seems
down.
okay. 8
Seems
feet, 16
okay.
seconds,
But it's open ocean swells, and then all of a sudden you have another swell that lines up, and that creates a 16 or 20 foot wave that
so it's
crashes
rogue
onto your boat.
So it's rogue because two of them kind of met and we didn't expect it.
It's like me yelling in one direction, and then all of a sudden you chime in and start yelling in the same direction.
Got it.
That can also, you can also be tracking a swell through the Pacific Ocean, and you have destructive interference, where there's one swell traveling and then you have another swell where the peak of one wave of one swell meets the trough of another swell.
And they kind of cancel each other out.
They kind of cancel each other out.
Because it's just energy. It's similar to sound and light, where if waves hit each other, they lose energy.
Right. I mean, there are some places,
or gain it, depending on, I guess, if they're aligned.
So check this out. In Santa Barbara, there's a wave called the Rincon, and it's a really good wave, but it doesn't get any south swells. And the reason for that is that the south swells will be coming up California, and then all of a sudden they hit the Channel Islands. And the Channel Islands act as like, picture me yelling and I yell at a house, right? My sound waves can't get past that house.
Right. You might hear it around the corner of the house, but probably not as well as if you were standing at a window in the middle of the house.
Exactly. So it's all, land masses are affecting it. The bathymetry is affecting the direction. If I'm yelling in one direction, it's going to affect how the wave hits the coastline. It's going to affect how it hits the reef.
So what we're really talking about when we talk about all this, we're talking about the amplitude and the period and all of these different things. Aren't we just talking about like the power of a wave or a combination of those waves?
Very much, yeah. We're talking about the power as well as the direction, right? So if I tell you that a swell is coming in at 295, right? If you look at a 360-degree compass, and it's coming in from 295, right? That's coming in from a northwest. That's going to hit the coastline at a different direction from a swell that's coming in at straight south 180 degrees. That's coming from a different,
so if it's coming in
part
kind
of the world.
Like shallowly or coming in perpendicularly, that's going to change what the wave looks like when it hits the shore.
Absolutely.
I mean, this gets really, really complicated, and it seems super simple. You're standing on the beach, and all you can think of is like, wow, these waves are really pretty. But in reality, all of these different waves of energy they kind of remind me of when you think of cosmic rays, or you think of all of these different waves that scientists are talking about, people who spend their whole career studying waves, we're watching that manifest on the ocean. That's kind of mind-blowing to think about. And if we could map all of that, it would probably look insane. If we could map every wave going through the ocean.
Oh, absolutely. I mean, this is all available online. You can look right now at a global graph of the Earth, and you'll see swells moving, down across the roaring 40s, and then they'll move up. Like, our technology has gotten pretty good. So, it's gotten to the point where meteorologists will be able to tell you how a swell is going to be that's just forming off of New Zealand and how it's going to affect California. So the roaring 40s, if you ever heard of this, it's the 40th degree of latitude in the southern hemisphere. Okay. And the reason a lot of swells will pick up steam down there is because there's no land-mass to interfere with the swell. So that's where they get all this energy, and then lots of times they'll track north, and a swell that formed down there will then hit Tahiti. Maybe it passes by Tahiti and it goes up towards Chile or up towards California. I mean, all these swells have different degrees.
Right.
And some are more predominant than others. Like right now we're in wintertime, so a lot of our swells are coming off of the Aleutian Islands or off of the Kamchatka Peninsula because that's where there's big temperature differences.
Yeah.
But they're coming from really far away. So if you're standing on the beach and you can look at a wave, and if you're on a pier and you're looking at the peak of one wave and then time until the next peak comes, and if it's over 15 seconds or something like that, that means that it probably came from really far away.
That's so neat. When it comes to like talking about waves, really what we're saying is like kind of everything is a wave. Like everything in the ocean is a wave. All the sound you're hearing are waves. The way waves move through the air, and I mean, you can
That's not hippie talk either.
No, it's not.
Science talk.
It's science talk. And you could even say that El Nino is a wave because El Nino has a dip in pressure, and then there's a La Nina, which is a high pressure system.
It's the opposite.
It's going to continue moving. Right?
Yeah, and that's how scientists can predict El Nino. That's why people, before this winter started, they said El Nino is happening this winter.